My name is Jarek Francik. I'm from Kingston University, London, and I'm going to talk about activity networks and critical path analysis. The objective of this method is to schedule all the activities within your project by determining for each activity its earliest possible start time, EST, and its latest possible start time, LST. The difference between these two times is called float, and it indicates how much each of these activities could be delayed without affecting the final project completion time. In every project, there is a number of activities for which this float or tolerance will be 0, and we say that these activities lie on the critical path. Any delay in the critical path will directly impose the same delay for the entire project. To draw the activity network of a project, we need a list of all the activities. You can see them here labeled from A to K. We usually don't use the label I because it would be a bit confusing with J. For each activity, we determine the preconditions or the set of other activities that must be completed before the given activity can start. As you can see, there are no preconditions for activities A, B, and C. This means that these activities can start immediately after the project initiation. As for the activity D or activity E, both of them have to wait until the activity B is completed, and only then you can go ahead with D and E. Similarly, for example, activity G has to wait until the activity D is completed. If you look at the bottom of this table, the activity K has two preconditions. It means that you have to wait until both of these activities, E and G, are completed before you go ahead with the activity K. One more piece of information that you can find in this table is the duration for each activity. This table will be used directly to create the activity network, in which every activity will be shown in a form of a node. This node is a bit complex. It looks like this. So for every node, you put its name or label and 4 pieces of information: the duration of this activity in the lower left hand corner, then going clockwise, EST or the earliest start time, LST, the latest start time, and finally float. So let's start with our drawing. I have put the table of activities conveniently in the corner of the screen, and I can start building the network with putting the start node on the left-hand side of the screen. Now we can choose all those activities that have no preconditions. These are activities A, B, and C. We simply put them next to the start node. Please note the node name inside each of the boxes. The lines indicate that each of the activities A, B, and C may follow immediately after the start node. Technically, we should use arrows here, but most usually we simply put straight lines and we assume that the flow of activities is either from left to right or top to the bottom. We also put the duration into each of the activity boxes. For the start node, it's always 0. For every other node, the values can be easily found in the table. Now we are ready to move on to the activities D and E. According to the table, the precondition for both of them is the activity B. So the activities D and E will follow immediately after the activity B. Here it is. There is no activity F. The letter F is quite often omitted to avoid confusion with the letter E. So let's move on to activities G and H. For both of them, the precondition is D, so they will simply follow the activity D like this. Next in the line is activity J, which follows after A, like this. And finally, the activity K is a little bit more complex because it has two preconditions, activity E and activity G, which may be shown in this way. We are almost finished, but we cannot leave any of the nodes without the line outgoing from this node. So what we need now is the finishing node, which should follow every activity that is not finished at this moment. This is the activity network with all the activities in it, ready to start the calculations. This slide is a recipe for all the remaining calculations we have to do. We will calculate the earliest start time, the latest start time, the float, and then we will determine the critical path. Back to the activity network, we will now calculate the earliest start time, or the EST, for each activity. This calculation starts with the start node, goes from the left to the right, and finishes with the finish node. The EST is normally shown in the upper left-hand corner of each activity box. With the start node, it's easy. The EST, the earliest start time, is always 0. For every other activity, the recipe is shown in the top of the screen. Take the EST, earliest start time, of any activity. Add the duration of this activity, and you'll get the earliest start time of the next activity. Look at the start node. Take the earliest start time, 0, plus the duration, 0, is the earliest start time of activities A, B, and C, 0. Look at the activity A. The EST of 0 plus the duration of 16 makes the earliest start time for activity J 16. Now look at the activity B. Its earliest start time is 0, plus the duration of 20 is the earliest start time for activity D, 20. A similar calculation may be done for activity E. Now let's get back to the activity D. Its earliest start time is 20. Add the duration of 15 and you will get 35 as the earliest start time for activities H and G. The next point is a bit more tricky. To calculate the earliest start time for activity K, we can go either from the activity G and get 35 plus 3 is 38, or from activity E getting 20 plus 10, 30. Which of these two numbers should we take, 30 or 38? The earliest start time of activity K may be either 30, because that's the time we have to wait until the activity E is completed, or 38. This is the completion time for the activity G. Of course, both preconditions must be completed, so actually we have to choose the maximum value of these two. If you look now at the top of the screen, you will see another part of this recipe which shows that in case of multiple incoming paths, always take the maximum value. The maximum value in this case is 38, so 38 is the EST for the activity K. A similar case we now have with the finish node, the only node left without the earliest start time. The incoming values are 30, 30, 51, and 50. The maximum value of them all is 51. Therefore, 51 is the earliest start time of the finish node, and in fact, it is the duration of the entire project. This is the earliest time in which the project can be finished. Now we have completed the calculation of EST, the earliest start time. Let's move on to the latest start time, LST, not LSD. LST is the latest time in which you can start any activity so that not to cause the entire project to delay. This calculation starts at the finish node, and then it is developed from the right to the left until the start node. With the finish node, the latest start time is the same value as the earliest start time. For any other activity, again, the recipe is shown in the top of the screen. Take the LST, latest start time of any activity, subtract the duration of an activity that was before that activity, and you'll get the latest start time of this activity. So, take the finish node, its latest start time is 51. The duration of the activity J is 15. 51 minus 15 is 36, the latest start time for activity J. 36 minus the duration of activity A, 16, is 20, the LST for the activity A. Similarly to this, 51 minus 30, the duration of activity C, is 21. 51 minus 16 is 35 for activity H. 51 minus 12 is 39 for activity K. 39 minus 3 is 36 for activity G. And 39 minus 10 is 29, the latest start time for activity E. The next one will again be tricky. For the activity D, we can either calculate the latest start time of H, 35, minus 15 is 20, but on the other hand, the latest start time of activity G, 36, minus 15 is 21. The latest start time of activity D could either be 20 to be in time for starting the activity H, or 21 to be in time to start the activity G. Because we are talking about the latest start time, this time, as you probably guess, we should take the minimum of these two values. As you can now see in the top of the screen, in case of multiple outgoing paths, always take the minimum value. The minimum in this case is 20, and this is the latest start time for the activity D. There is a similar case with the activity B, for which the latest start time may be either 0 if you look at the activity D, or 9 if you look at the activity E. Of course, the minimum is 0, and so this is the latest start time for activity B. Looking at the start node, the incoming values now are 20, 21, and 0, and the minimum is 0. In this moment, we have completed the calculation of the latest start time, and we can move on to the next stage. We are now entering the final stage of the whole process, calculation of the float. If you look at the node J, its earliest start time is 16, but its latest start time is 36. The difference between the two is 20. If these were days, it leaves enough time to go for a Caribbean vacation, come back, and still get the job done in time. This difference, LST minus EST, is what we call float, and this is 20 in case of the activity J. For all other activities, the calculation is quite easy. For each activity, the float indicates the amount of time for which the activity may be delayed without making the whole project delayed. For some activities, like A, J, and C, this amount of time is quite high, 2021. But for others, like B, D, and H, it is as low as 0. This means that there is no tolerance here for any delays. These activities are critical for the entire project because any delay in any of these 3 activities will definitely impose a delay to the project completion time. All nodes with float equal to 0 make the project critical path. Every project has at least one critical path, and some may have more than one. It is a crucial concept for project management and especially for resourcing. These were activity networks and critical path analysis presented by Jarek Francik, Kingston University, London.